Hello, everybody. I am Shan, a graduate student at Nankai University. Today, on behalf of our team, I am honored to have the opportunity to present our recent work called Non-Single Silver Bullet, Measuring the Accuracy of Password Transmitters. Passwords firmly remain the dominant mechanism for user access control on the web. A password transmitter provides real-time strength feedback upon user registration and password change. Web service equips a password transmitter to encourage users toward secure passwords. Over the past decades, academia and industry have made impressive efforts to design PSMs. Although dozens of PSMs have been proposed one after another, it is unclear which one is more accurate. For example, as shown in this figure, we will measure the strength of this password. Different PSMs provide various feedback. But which PSM is more accurate? In this paper, we propose a systematic evaluation framework that is composed of 4 different dimension criteria to rate PSM accuracy, and 2 password guessing scenarios, as well as 6 guessing strategies. We utilize our evaluation framework by rating 12 state-of-art PSMs, leveraging 14 real-world password datasets. Moreover, we provide 3 recommendations to help improve the accuracy of PSM. Before starting, I will introduce password guessing scenarios. According to where the attack is performed, password guessing scenarios can be divided into online and offline guessing. In online guessing scenarios, the attacker will check her guesses by constantly attempting to log in as a normal user. A server can reduce her advantage by limiting the login rate and local accounts when the failed attempts exceed a threshold. Therefore, an online attacker can only perform very limited guessing attempts. An offline attacker has obtained a password file, so she can locally verify her guesses. Thus, it is not difficult for her to make more than billions of guesses. As the attacker in different guessing scenarios suffer from essentially different constraints, the focus of a PSM should also differ accordingly. In the online guessing scenarios, a PSM should accurately detect popular passwords. But in offline guessing scenarios, a PSM is to prevent easy-to-crack passwords from registering as much as possible. So, there is no single silver bullet metric for evaluating PSM accuracy. In online guessing scenarios, attackers can be divided into categories. For an attacker well informed of the target password distribution, the sensible strategy is to prioritize trying the most popular passwords. We call here a knowledgeable online attacker. In contrast, for an attacker unaware of the target distribution, her sensible strategy is to traverse common popular passwords, and we call here a general online attacker. Due to the limited attempts allowed in online guessing scenarios, a PSM should accurately detect popular passwords, especially the most popular passwords. Consequently, popular passwords are weaker because they are tried before unpopular ones. That is, the higher the frequency of a password, the lower its strength. Based on this guessing strategy, an ideal PSM can be regarded as a good benchmark. for evaluating PSM accuracy in online against scenarios. For it adopt the frequency of the passwords in a real-world dataset to indicate their strength. The accuracy of a PSM can be measured as its distance from the ideal PSM by calculating the correlation between its evaluated strength ranked list and the referred ranked list of the ideal PSM. Classic experiment correlation coefficients are not suitable for measuring the accuracy of PSMs because they mistakenly treat all passwords as equally weighted data points. Since the strength evaluation error of frequent passwords will impact more accounts, it is necessary to weight the correlation coefficients. So, we take weighted Spearman correlation coefficients to measure the accuracy of PSM in online guessing scenarios. Here, we show the evaluation results of 12 state-of-art PSMs in online guessing scenarios. We can observe that in online guessing scenarios, fuzzy PSM performs the best, followed by the XVBN. Pattern-based and attack algorithm-based PSM need to be adapted to evaluating passwords in different languages. Next, let's turn our attention to offline guessing scenarios. According to adopted guessing algorithms, offline guessing attackers fall into three main groups: brute force, dictionary-based, and probability-based offline attackers. It should be noted that real-world attackers are likely to try all these three guessing strategies to achieve higher cracking rates, and we call such a powerful attacker a combined attacker. Unlike online guessing scenarios, an offline attacker can perform large-scale guesses on offline guessing scenarios. She doesn't care about whether any specific guesses is hit or not, but pursues a higher cracking rate on the whole on the constraints of computing resources and time. So, the main focus of a PSM is to accurately distinguish passwords that are easily to be cracked. Specifically, a good PSM should give differential strength rating between the cracked and the remaining passwords. So we use scale diversity to quantify such difference to measure the strength accuracy, PSM accuracy in offline guessing scenarios. Here, we summarize the scale diversity of leading PSM under various attacking strategies and identify the best PSM on each guessing strategy with the background color. We find that in offline guessing scenarios, multi-PSM generally perform the best. Markov PSM and the XVBN are the most accurate PSM and probability-based and dictionary-based guessings, respectively. Commercial PSM usually adopt intuitive color bars with bins or scores and its feedback to promote user understanding of password strength. Now, let's think about the question: how will the accuracy of a PSM change when its no-bin strength feedback is converted to easy-to-understand bins or scores? So, we propose a new metric, namely precision, to answer this question. Here, we present the detailed calculation process of precision. Further, we note that strength misjudgment in different directions would have different security impact. The weak to strong misjudgment will mislead the user that their weak password is strong enough, which has much more negative security impact than strong to weak misjudgment. So, we set reconciled misjudgment parameter, beta, at 0.8, corresponding to more serious misjudgment, weak to strong, and propose a new metric, precision security. We adopt our proposed precision and precision security to evaluate 12 PSMs and show the results here, and identify the best PSM under each guessing strategy with the background color. In offline guessing scenarios, multimodal based multi-PSM has the highest precision and precision security under the combined guessing attacks and perform the best. The XCVBN also shows its advantage on dictionary-based and probability-based guessing strategies. From our experiments, we gain a number of insights and provide a few suggestions to improve PSMs. Firstly, we find that adaptive score conversion methods can be used to facilitate PSM application. Secondly, we noted that PSM can be effectively integrated to perform better. Finally, through cross-language evaluations, we also provide the evidence that PSM need to be modified or adapted to accommodate different languages. That's all. Thanks for your attention. Now, we have several minutes for question and discussion.